Welcome to Naming Elements and Covalent Compounds. So we can identify a substance by either a unique name or by a chemical formula. And we need a system for naming chemicals so that we don't come up with duplicate names and so that other people know what the name means. And there are a few substances, not very many, but a few, with non-systematic names. So these are also sometimes called common names. And you just need to memorize these. So water is H2O, and ammonia is NH3. There are a few others as well. Now we can divide the substances into two broad categories. Organic substances, which contain carbon and hydrogen, and sometimes other elements, and inorganic substances, which do not contain both carbon and hydrogen, although they may contain one or the other. Note that there are a few exceptions to these rules, but we'll deal with those later. You're going to learn how to name organic substances in an organic chemistry course. We won't cover that here. But in this course, we're going to be concerned with naming inorganic substances, so those that don't include both hydrogen and carbon in general. We will further divide inorganic substances into smaller categories. And note that we will discuss in Chapter 7 how to name elements, binary covalent compounds, and binary ionic compounds, whether they contain monoatomic ions or polyatomic ions. Now recall that an element is a substance that is electrically neutral, which means it has a charge of 0, and it contains only one type of atom. The name of the substance is simply the name of the element. For example, the element composed of electrically neutral atoms containing 20 protons is called calcium. Calcium is a metal, and the chemical formulas of metals are written as if they were monoatomic, so just Ca. Chlorine is a nonmetal, and at room temperature and pressure, it is most stable in neutrally charged diatomic molecule Cl2, chlorine gas. Sulfur is another nonmetal, and at room temperature and pressure, it's most stable in molecules with 8 sulfur atoms covalently bonded together, so S8. Note that for both chlorine and sulfur, the name of the substance is simply the element, so we still call this sulfur, even though the smallest particles contain more than one atom of that element. Some elements have more than one stable form, and these forms are called allotropes. For example, electrically neutral carbon can form a few different allotropes: graphite, diamond, and fullerenes. Graphite structure looks something like this, where we have planar sheets of carbon atoms bonded together in hexagonal rings. Diamond looks like this, where each carbon atom has 4 bonds to its neighbors. They're in a tetrahedral geometry, which is sort of a pyramidal shape. And then fullerenes, we have a number of different fullerenes. This one happens to be carbon 60, so C60. The most stable form at room temperature of carbon is graphite. So graphite is generally designated as simply carbon, so just simply C. Diamond is generally designated as C, and then a subscript of diamond indicating the phase is not graphite, it's diamond instead. Fullerenes are generally designated as C with a subscript N, where N indicates the number of carbon atoms contained in one fullerene molecule. For example, on the last slide I showed you the C60. That happens to be Buckminster fullerene, named after Buckminster Fuller, who designed geodesic domes, of which the C60 resembles a geodesic dome. And note that while the chemical formula may indicate whether the element is monoatomic, diatomic, or polyatomic, the name does not. So that means that it's up to you to know the most stable form of each of the elements, because the name isn't going to tell you. So for all of those diatomic elements that you should already have memorized, you need to know that, say, chlorine or oxygen or nitrogen in their elemental states exist as Cl2, O2, and N2. For elements, this generally isn't too big of a problem because there are only a few that aren't monoatomic, but for the millions of compounds, we need a more descriptive naming system called nomenclature. Now remember that a compound is composed of more than one element. So we can't simply call the compound by the element name because we're going to have more than one element involved. And we have 2 broad types of compounds based on how they're bonded: covalent compounds and ionic compounds. Now covalent compounds contain 2 or more nonmetals bonded together by sharing electrons. The bonds within a covalent compound within covalent molecules are very strong, but the bonds between covalent molecules are far weaker in comparison. Substances that are solids at room temperature may either be ionic or covalent compounds. Remember that ionic compounds have a complete transfer of electrons, unlike the sharing that goes on with covalent compounds. And substances that are liquids or gases at room temperature are almost always covalent compounds. That is, the melting points and boiling points of ionic compounds are usually quite high, in the thousands of degrees, and thus they're almost always solids at room temperature. So something like table salt, that's a solid at room temperature. Ionic compounds are composed of an array of ions called a lattice, bonded together by electrostatic attractions, which means that the ions are held in place because the positively charged cations and negatively charged ions, anions, are attracted to each other, and each ion generally has a large number of oppositely charged ions around it. So, for example, in a sodium chloride lattice, we have a sodium ion, and it has 6 chloride ions around it, one to the left, one to the right, one above, one below, one in front, and one behind. And the same thing is true for each of the chloride ions. Each of the chloride ions has a sodium ion, so positively charged ion, on one of the 6 sides around it. Covalent compounds and ionic compounds have different nomenclature, different naming systems, and this means that in order to name a compound, we must know which of the 2 types of compounds we're trying to name. So now let's examine the 2 types of bonds and the compounds that they form. There are 3 types of chemical bonding: metallic, covalent, and ionic. Metallic bonding is only seen between metal atoms, and because metallic bonding is not involved in the formation of compounds, most first-year chemistry courses spend very little time covering metallic bonding, and thus we're going to mostly ignore metallic bonds. Covalent bonding involves sharing of electrons between the 2 atoms involved in the bond, and ionic bonding involves the complete transfer of one or more electrons from one atom to another, creating 2 ions, one positively charged and one negatively charged. The positively charged ions are called cations, the negatively charged ions are called anions. Let's use the following rules to predict whether the chemical bond is covalent or ionic. A bond between 2 nonmetals is covalent. A bond between a nonmetal and a metal is ionic. A bond between 2 metals is a metallic bond, but as we've discussed earlier, we won't spend much time talking about these. I know that there are a few exceptions to the above rules, but these rules work in most cases. Remember that you should have memorized all of the nonmetals and the metalloids, which we're generally going to ignore in naming and bonding purposes, in first-year chemistry courses at least. If you can't name or use a periodic table to name all of the nonmetals and metalloids, you need to stop now and memorize them right now. So pause the video, make sure that you can do that. Remember that of the 18 nonmetals, 17 if you include acetine with the metalloids, then 6 are noble gases, which very rarely form bonds. So there are only 12, or 11 if you're including acetine with the metalloids. There are only 12 nonmetals left, and bonds between these are almost always covalent. If the compound contains one of these nonmetals and another atom that is not a nonmetal, in other words, it's a metal, then the bond between them will almost always be ionic. So, we have 2 types of compounds then: covalent compounds and ionic compounds. A compound is covalent compound only if all of the bonds that it contains are covalent. If any of the chemical bonds in the compound are ionic, then it is an ionic compound. And this is true even if it also contains many covalent bonds. Now, a binary compound is a compound containing exactly 2 elements, or exactly 2 particles. Note that a binary compound may contain more than 2 atoms of those 2 elements. A molecule containing exactly 2 atoms is a diatomic molecule, which may or may not be a diatomic compound. A binary compound. Now, a binary covalent compound is a covalent compound containing exactly 2 elements bonded covalently, and often binary covalent compounds containing hydrogen are given non-systematic names, so these are common names like water and ammonia. So, methane is CH4, water is H2O, ammonia is NH3. And this is because these are very common compounds for us to be using, and that means that they were named before we really knew very much about chemistry. They were named hundreds or thousands of years ago, and thus we didn't know their chemical structure. We didn't know what elements were in them, so we couldn't name them systematically, and these names are so common that they've stuck. So note that each of these compounds can be named systematically as well, but we almost never actually use the systematic name to refer to them, and it's generally considered poor practice to do so. We could call water dihydrogen monoxide instead, but nobody really uses that term. We just use water because everybody knows what water is. In naming binary covalent compounds, we use the root of the nonmetal name. So that means that we need to know what the roots are. You need to memorize these. So the roots are listed here. So here we have each of our nonmetals, ignoring the noble gases. So we only have 12. We've got hydrogen, and the root there is hydr. Carbon is carb. Nitrogen is nit. Oxygen is ox. Fluorine is fluor. Phosphorus is phos. Sulfur is sulf. Chlorine is chlor. Selenium is selene. Bromine is brome. Iodine is iode. And astatine is astat. To name a binary covalent compound, then you follow these rules. The name contains exactly 2 words with the format prefix, element name, space, prefix, root, IDE, so I. For covalent compounds containing oxygen atoms, the second word is prefix oxide. So this rule takes precedence over the below rules. The first word contains the name of the element that is further to the left on the periodic table. If both elements are in the same group, so in the same column on the periodic table, then the first word contains the name of the element closer to the bottom of the periodic table. So that first word is that element closer to the bottom left side of the periodic table. The second word is that element closer to the top right. So that second word contains the root of that second atom name. So the atom that is closer to the top right, we're using the root of the atom on the right. We're using the full name of the atom on the left, the element on the left. So that second word contains the root of the second atom name plus the suffix IDE. So oxygen becomes oxide, fluorine becomes fluoride, and so on. Each word contains a prefix indicating the number of atoms of that element, and these prefixes are from the Greek words for each number, which I have on the next slide. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca, and they do go on from there, but these are the 10 that you need to know. Note that the mono prefix is not used on the first word, but it is used on the second word. If the element name or root begins with a vowel and the prefix ends in an O or an A, then the ending O or A is dropped from the prefix. And note that there are only 3 such elements: oxygen, which is oxide, iodine, so iodide, and astatine, which is astatine. So also note that while dropping the O or the A at the end of the prefix is technically optional, it almost always makes the name easier to pronounce, so I highly recommend doing this. It's also important to note that the di and tri prefixes never drop the I when the element name starts with a vowel, even if the element is iodine. So you're only doing this with element names that start with a vowel, so only those 3. And you're only doing this with those prefixes that end in O or A. You're not doing it with di or tri, so those prefixes that end in I. So let's name a few examples. So I want you to pause the video as soon as I change slides and write down what you think the name of the compound is, and then, and only then, unpause and see if your answer matches mine. So here we have NO, N2O, NO2, N2O3, N2O4, and N2O5. So pause the video. NO is nitrogen monoxide. Note that we've dropped the O on the mono, so we don't say nitrogen monooxide. We also don't have the mono in front of nitrogen. It's not mononitrogen monooxide because mono is not used in that first word. It's only used in the second word, if we only have one of that second element. N2O is dinitrogen monoxide. NO2 is nitrogen dioxide. N2O3 is dinitrogen trioxide. N2O4 is dinitrogen tetroxide. Again, note that the A has been dropped. N2O5 is dinitrogen pentoxide. Again, it's not pentaoxide, although technically that is an option. It is technically legal for you to do this, but pentaoxide is more difficult for us to say than pentoxide is. So here's another set. Pi3, SCl2, NF3, SCl4, ClF3, P4O10. I'm going to pause the video now and name each of these. Pi3 is phosphorus triiodide, SCl2 is sulfur dichloride, NF3 is nitrogen trifluoride, SCl4 is sulfur tetrachloride, ClF3 is chlorine trifluoride, P4O10 is tetraphosphorus dicoxide. So, I want you to make the flashcards listed in the book for this lesson and memorize them. Do that right now. That was naming elements and covalent compounds.